In this video, we're going to analytically solve the explicit Riemann sum of a function. The Riemann sum is a number of rectangles used to approximate the area underneath a curve. This is an example of a left corner sum, where the left corner is equal to the value of the function, which in this case underestimates the true value. This is an example of a right corner sum, which in this case, where the right corner is equal to the value of the function. This is the example we're going to use this is the case we're going to use in our example. Here we have n equals 2. We have the area subdivided into two rectangles. If we use 4 rectangles, n equals 4, you notice that the amount of error becomes very small, or becomes smaller. Further, if we continue and set n equal to 8, if we subdivide the area underneath the curve into 8 rectangles of equal width, then our area becomes progressively smaller. In our example, we're going to use the function x squared plus 3 dx from 0 to 4. Our limits thus are from 0 to 4. In order to get the feel for what we're doing here, I would first like to find the area of these using n equals 2. To find this, we need to find the width of the rectangles, and since we have 2 and they go from 0 to 4, that's going to be a width of 2. The height right here, or the x value right here, will be 2, and here it will be 4. Because these are equal subdivisions. So we put x equals 2 and x equals 4 into our function for the height. Because base times width times height is equal to the area of a rectangle. So the area is going to be, we'll do x squared, where x is 2, plus 3, times a width of 2, plus x squared, where x equals 4, plus 3, the width of 2. This will give us 4 plus 3 is 7 times 2, 14. 4 squared is 16, plus 3 is 19. 19 times 2 is 38. 38 plus 14 equals 52. When we actually solve this explicitly, we'll see that this is a larger value than the correct value, but it is at least the same size, roughly, same order of magnitude. I do this purely to show an example for a finite sum, how to solve this. Now we're going to take the limit as n goes towards infinity of a Riemann sum, where we're going to sum all of the rectangles from rectangle 1 to rectangle n. So we'll have n number of rectangles. We'll sum their height. Well, the area of each rectangle will be the height of the rectangle, x star, f of x star, times the width of the rectangle. The rectangle width is given by b minus a over n. Now, in our case, we're summing from 0 to 4. So 0 equals a, and 4 equals b. We have 4 minus 0 over n, or simply w equals 4 over n. Likewise, x star. X star gives us the value of the x value of the right corner of the rectangle. So x star equals a, that's where we're starting from, plus I w. I is the variable of summation. This will increment by 1 for each successive rectangle. Now in our case, a happens to be 0, so we get 0 plus I. W is 4 over n. X star equals I 4 over n. Once again, I'm going to box this because we're going to use this in the rest of the problem. Now, we need to apply this into our sum. Limit as n goes towards infinity. We have a summation. I equals 1 to n. Our function is x squared plus 3. So I will include x squared, x squared plus 3 times the width. Our width in this case is 4 over n. Now what we need to do is we need to simplify this function, because n is not the only variable of summation is I. We can take everything but I out of the summation, not out of the limit though. So if I come down here, we have a bit more room. Limit, we'll take the summation of, let's expand this first. We'll have 64 over n squared, I squared, plus 12 over n. We can sort of simplify this by writing the limit of 64 over n squared, summation of I squared, from I equals 1 to n, plus 12 over n, summation simply 1, from 1 to n. Now this looks like a bit nasty, but there are functions for these that we can use. This value of this happens to be value of this part right here. So we have our limit 64 over n. Wait a second. N, this right here became an n squared because of that. The n should have made that become an n cubed. Be very careful with your n's. They will step back and bite you. So this is n cubed. That makes a big difference. This summation right here becomes n cubed over 3 plus n squared over 2 plus n over 6. And our second term here, 12 over n, summation of, from 1 to n of 1, well, we're summing 1 n number of times, so this right here, it really is just n. So we get 12n over n. n over n is 1, So this really just becomes $12. Okay. Now, it's a matter of evaluating the limit. We can simplify this by writing, we have plenty of room to write, 64 over 3. Of course, as n goes towards infinity. We have 32 over n plus 32 over 3 for n squared plus 12. As n goes towards infinity, both of these terms drop out. We have n in the denominator. What we're left with is 64 thirds plus 12, which we can simplify to be 33 and a third. If we wish, we can double check this by using the rules we'll learn about shortly to find the to explicitly evaluate this function without the complicated Riemann sum. For just to show how this is done, I will do this quickly on the next page. We will write summation, the integral from 0 to 4, x squared plus 3 dx. Now, using the integral power rule, we can write 1/3 x cubed plus 3x, evaluated from 0 to 4, plus some constant. If we wish, to double check this, we can take the derivative of this and see if we obtain that, which we do. If I plug these values in, I get 1/3 4 to the power 3 plus 3 times 4 minus 0 minus 0, from our 0 term. Our c's cancel out. This indeed becomes 64 over 3 plus 12, which is 33 and a third. The Riemann sum, although it is much longer and much more painful to do, frankly, it is a pain. It is, however, important. It is essential to understand. I mean, this will get you the answer quickly, but this is understanding the answer. You can't always do this. Now, in the examples we're going to do, you will be able to, but sometimes you have to fall back to the original meaning of it. And calculus is one subject in particular where understanding the meaning is very important.